Yeah, thank you very much. I'm Barry Fell. I'm with the MITRE Corporation. The reason for that is I sat next to George Benke about a year ago and something rubbed off on me, so finally saw the light. So I'm going to talk to you about a very important problem, spectrum sharing, and I'll give you some motivation for that. And then you won't find too many equations. I don't think you're going to find any equations in this talk. But then I see this as a big opportunity for the harmonic analysis community, and I'll discuss that at the end. So if I can, here we go. So basically, I'm going to cover these topics, but really let me start by talking about the Norbert Wiener Center. I was introduced to the Norbert Wiener Center about 10 years ago by Greg Coxon, who introduced me to John Benedetto. And one thing we have in common is that we both have high regard for Norbert Wiener. And he wrote a book in 1948 called Cybernetics, which really set the stage for the modern computer revolution. But in addition to that, he also wrote a companion book called The Human Use of Human Beings. So he also had a very strong social conscience and tried to point out with all the automation and machine learning that we have today, that's going to affect the labor force. So he brought that up very early, in the early 50s. And one of his famous quotes that comes from the introduction of the book was that some of the most fruitful areas to work in science is where you bring different disciplines together. And basically, that's been the story of my career. So what I'll be doing is defining and laying out the elements of a problem that you can contribute to the solution to. So my message is simple. Commercial wireless, the rapid growth of that and the use of spectrum has really grown exponentially. That spectrum sharing, that is getting two different types of systems, say a radar system and a communication system, to work together within the same spectral region, sharing that spectrum, will actually open up how much spectrum we can actually use in the future. That I'll define the various functional elements that will go to a solution for this spectrum sharing. And then, as you'll see, the solution, I think, depends a lot on the kind of work that the mathematics community does. So here is spectrum. When we pick up a cell phone and we call somebody, I don't think we really appreciate exactly what we're doing. But this thing we call the spectrum really serves a lot of masters. It's not only the cell phones, but it's also things like radio astronomy, radar. There's a number of space communication systems, and there's going to be now a surge for commercial synthetic aperture radar in space. So the question is, how do you basically assign spectrum to all these systems so that they don't interfere with each other? Well, this is the current way we do it. The world is broken up into 3 regions. The US is in region 2, and this is done by the International Telecommunications Union, which is basically a consensus of all the countries on Earth. This is the way we divide up spectrum in the US. This comes from the FCC, and the interesting thing is that the focus of the area that we're talking about is really this region, which is somewhere in the order of 300 megahertz, not quite to 30 gigahertz, but it's certainly within this region. This is a sweet spot for communications. It also happens to be an important spot for radar systems to operate. So what is the challenge? Well, how do you combine the waveforms of different systems to make sure that they don't interfere with each other? And here I've tried to indicate the space that this problem is defined in. Basically, each of these systems has a number of degrees of freedom. There's a spatial degree of freedom. Where am I located with respect to other systems? Also, what kind of antenna do I have? Am I transmitting in all directions, or do I have a directive antenna, such as a radar system? And also, there's a temporal portion of this as these systems operate, in not only space but also time. And then there's the spectral component. And right now we focus primarily on separating these systems in spectrum, but as we get more and more dense use of the spectrum, the question is, can we have these different systems share that common spectrum? And that means finding ways to separate these systems from interfering with each other in space, time, frequency, and then here's some other degrees of freedom. The waveform itself, polarization. So it's a multi-dimensional space, not only because you have the degrees of freedom with each system, but then you have multiple systems that are trying to operate in the same space. So what is it going to take to try and solve this problem? From a systems engineering perspective, the way we look at this problem is the first thing we need to do is to characterize how the spectrum is being used. And we'd also like to do this in real or near real time. So once we know what's going on and we continually update that in real time, what is the architecture that's needed to support that? Once you have that architecture in place to achieve real time, then how do you make decisions with all these nodes and all these degrees of freedom? And the other aspect of that decision theory is that you're making decisions under conditions of uncertainty, because when you do your usage characterization, there's errors associated with all those parameters that you're measuring. Also, in order to affect this, the different nodes have to talk to each other and be informed about what they're doing. So you need a highly reliable control network that keeps everything together. However, being the real world, there may be times when that control network fails either in a certain location or a region. So another big issue there is if I can't talk to my neighbors, how do I operate autonomously until I can continue to communicate with these other nodes again? So these are really the foundations of trying to solve this problem. And now let me go into a little more detail about each of these. This is an overview of how that system would operate. As I say, you need to characterize the spectrum first, then you reason based on the fusion of that data to make certain decisions, and those decisions have to entertain the uncertainty in that data, and then you have to allocate the right operating parameters to the different elements of the system. So there's a simple way of saying this. I have to observe, orient myself, characterize, decide what to do, and then actually act. And if you notice, that's OODA, UDA, and that's called the UDE Loop, and I'll speak about that in a few minutes. So what are the features of characterizing the spectrum usage? Well, you certainly want it to be complete. You want it to be as complete as possible because you have many degrees of freedom that you can use to separate these signals. Also, an important part of this is how do you do your error estimation? What is the accuracy with how I measure, but also how do I characterize the uncertainty in this characterization? And then it also has to be timely if I want to do this in real time. So it's an iterative process, and I want to continue to update that. So here's an illustration of how this might all pull together. Basically, we're sensing data. Notice that we're talking about a distributed set of sensors. These sensors could be specialized sensors, or it could be the systems themselves, looking at the frequency region that they cover. So all this data is collected, it's fused and analyzed, and then it basically has to be put into some frame so I can understand exactly what I have. And then, that characterizes where I am in time with respect to characterizing the spectral use. One part of this is because I have various nodes and I want to find how they interfere with each other, is I have to have a pretty good idea of how that RF radiation is propagating from one point to another in various environments, because I basically have terrain that I'm going over. There may be hills, there may be valleys. So this is one of the primary sources of error in being able to do accurate characterization of the spectral interaction between nodes. But then the other thing, if I truly have a distributed system with a control network, then I can continually update how these sensors should be used, what sensors should be used, what areas they should focus on. So this is a closed loop characterization of spectrum. And it also, as I say, the key, it has to be done in real time or near real time. So this is the UDE Loop. It was introduced by John Boyd in the mid-90s. And as I say, the key elements of the UDE Loop is to observe, to understand those observations, bring understanding to those observations, so you can start to make decisions. And then once those decisions have been made, then you want to basically disseminate the commands to the various nodes so that the whole system operates properly. So this brings into question, what kind of architecture do I need in order to operate real time? So number one, notice that the environment we're going to be working in is congested because there's a lot of users of spectrum in a small area. So the architecture has to support doing the spectrum characterization. It has to be able to close this UDE loop in real time. And then it has to make the decision as to what information to send out to the various nodes. And that has to be done in such a way that this massive amount of data is distilled so it's actionable. So I can't just throw all the data onto a node. I have to tell that node precisely what to do. Also, we want to be able to make optimum decisions with respect to mutual interference. And we also need rapid feedback. That's part of the UDE loop to make this effective. And then we need to enhance the overall efficient use of spectrum. So the guide words here is that the whole should be bigger and more effective than the sum of its parts. By everybody knowing what they have to do in this overall context, you're actually increasing the overall way that you use, in this case, spectrum. So this is a potential architecture. This may not be a final architecture, but we know it has all the elements necessary. Notice that we've defined 4 generic levels. There's probably intermediate levels, but the most important are the devices or the nodes themselves. You bring nodes together. This is the first fusion level. And this will probably be done machine to machine. Then the next hierarchy is the machine to human interface. And then finally, various operators go to basically a top operator that overviews the operation of the entire system. So one question is, how do you relate these nodes? What nodes should be placed together so that they can be operated together? And it's not just the location of the node. What drives what nodes should be considered together is really the potential of their interfering with each other. So I could have a number of ground nodes that are localized. Certainly they've got to exchange information, but if I have an airborne or a spaceborne system, then I have to consider that also in this loop because they have a potential to interact and interfere with each other. And for each of these levels, we have our own OODA loops, and for each of those OODA loops, we have some type of response time that we're looking for. And at the lowest level, you're probably talking response times on the order of microseconds, milliseconds, and then that eases as you go up. So the other issue that we raised is how do you do reasoning under conditions of uncertainty? It's got to be very fast because you're trying to do this in real time. And the decision theory must take into account not only the spectrum characterization, but the spectrum characterization error. And then we also would like to be able to perform rapid detection of anomalous behavior within the spectrum, that we see a collision between a couple systems. How do we identify that so we can take action right away? And then we can also use this, as I say, the whole is greater than the sum of its parts, to re-affect how we do our estimation and characterization of spectrum and how we operate so that we maintain maximum effectiveness. So these are some of the technologies that currently exist to do reasoning under conditions of uncertainty. Neural networks, deep learning neural networks, these need to be trained. And also, if you can't identify all possible conditions, then what happens when a neural network sees a brand new condition? So they may not be the ultimate answer to this, especially in real time. Dempster-Schafer is a Bayesian approach that does take into account decisions under uncertainty. So that includes the errors associated with these different nodes. And then on top of that, these techniques have to take in all the physics associated with how a radar operates, how a comm system operates, and what the interference mechanisms are between those. So in order to affect all this, we said we needed a network to tie all these nodes together. That network also has to be distributed. And what are we looking for in that network? Well, it has to be highly available. It's got to be scalable. As we say, it has to be distributed so that a failure in one location doesn't affect it in other locations. And basically, another element of this is adaptive throughput. You want to design this in such a way that minimum data is transmitted between these various nodes. However, at times that you may need more exact information sent to the nodes. Other times, when you're like in a steady state, you want to minimize what that data is. So these are the elements of what that network has to do. As I said, there are probably going to be occasions when that network fails, hopefully not across the entire system, but certainly in various locations within the system. And then the question is, how do you still maintain system operation within the spectrum? So if that occurs, then you have to worry about how can a node operate autonomously in this congested region and still maintain a minimum of interference with other nodes. So these are some of the things that you have to consider. And one is that you probably resort to the lowest level of the architecture that we showed and see if there may be other ways that you can communicate between the nodes now that you're alone. But also there's been work done that looks at if I'm a node that's working autonomously, I still can sense what's going on around me. And as I do my things, I can see changes in what's happening around me, and I can adjust my performance to minimize any adverse effect to other systems. And then just to wrap up, these are other technologies that are important in order to support solutions to this problem. one big issue is how do you take big data and basically reduce the dimensionality, first of all, but also take that data and translate it so that a machine or a human can actually understand what direction they should go in or what decision they should be made, And then also, especially for human operators, how do you present that to a human being so that they can make a decision in a short amount of time, and that decision is a correct decision. Device ontology, I think, also plays a role here. How do you develop a way to characterize the performance and the characterization and the capability of all these devices, especially when they're different? You have different kinds of communication systems, different types of radar systems. The physics demands that you analyze all these systems mutually, so the ontology that you use really has to be broad enough to characterize all these systems. I mean, today, basically, we divide ourselves into different groups. I have a communications engineer, I have a radar engineer, I have maybe a space satellite engineer, and what we found is that you really are looking for somebody that can bring all these talents together. So the so-called stovepiping of specific capabilities really inhibits how you solve these problems. You really have to be much broader in your capabilities in order to work a lot of these problems. As a systems engineer, my job really is to lay this out sort of in the way I showed you so that various specialists can find their role in this. And one other key enabling technology is that devices in the future, and this is already happening, that they have to be much more agile so they can maybe hop around in frequency. I know there are a number of cellular systems that can go from one frequency band to another. So that brings me to describing what I see as an opportunity for harmonic analysis community. And yeah, I took a number of these off of a slide that John Benedetto showed about a year ago as to capabilities within the Norbert Wiener Center. But in general, I think these are areas that advances in technologies in these areas bring a lot to the solution of the problem that we discussed. Certainly how the waveform design between different systems, how do you reduce the dimensionality of big data, blind source separation. When I'm doing characterization of spectra, if I have a number of systems that are localized, how do I make sure I can locate and determine that there are a number of different systems and do that passively? We've talked about the decision theory under conditions of uncertainty. And then another important thing is that we see basically simulation being very important in this from the standpoint of we have a very complex situation. If I can run a number of different simulations that each would describe a different set of outcomes, if I can do that rapidly enough, that can aid in the proper decision as to how I basically set the various parameters. So what have I said? Number one, this is a very important problem in the commercial wireless industry. There is some spectrum sharing going on right now at 5 gigahertz and 3.5 gigahertz. I've tried to outline what we see as the critical system elements that are needed to solve this problem. And the opportunity for the harmonic analysis community is to take a look at the areas that, where techniques already exist. How do you combine these techniques, or are there new modalities that you can think of that are more appropriate to solving this problem? So there's been a number of people I've been working with over the years, and these are some of them. Gary Jasna is on the board of the Norbert Wiener Center, and there's always been a close relationship between the Norbert Wiener Center and MITRE, and I certainly really appreciate that. And guess that's, be happy to answer any questions.